Thanks for the nice introduction and welcome to my talk about influence of the corrosive sodium chloride solution in lifetimes of 1775 aluminum alloy under combined fatigue life in a very high cycle fatigue regime. The aim of the study shown is to get an understanding of the damage and the failure of components at low stress values and critical combination of stress. We are conjugated to experiments in lifetime in the high cycle and very high cycle fatigue area with a combination of low and high frequency tests with constant and variable amplitudes. The used material was 1775 aluminum alloy and a heat treatment of T651, and you can see here the shape form. It was machined from plates and polished. The measuring cylindric part is 10 millimeters length and has a diameter of 4 millimeters. This specimen shape is determined by the resonance condition of the ultrasonic device. You can this from the previous presentations. It is from the BOCO. Left you can see the ultrasonic, servo-hydraulic testing equipment, and here is the specimen. In this image you can see the ultrasonic test equipment, and the specimen is here, and you can see here the strain level, and the maximum is constant over the all range of the 10 millimeters. We measured a superposition of low and high frequency loadings. The carrier wave, the low frequency wave, is supporting from the servo-hydraulic load device, in my case MTS test cell device, and it has a square form with 0.4, 0.5 or 1 Hz. And superimposed is an ultrasonic random signal. It is not possible to make only one pulses. The minimum is 500 cycles or 25 milliseconds for one block. So one block of pulses needs minimum 25 seconds. In the test case, we have two different ultrasonic random sequences, one from 10 to 70 Pascal in green in this and this diagram, and the second 50 to 90 megapascal. Both are on the same Gaussian distribution with sigma 0.3477. The signal or the sequence from 10 to 70 megapascal contains 35 levels and above 1200 data points. You can see here the data points in order of the testing sequence. It is not sorted, it is random. And in red, the 50 to 90 megapascal with 21 levels and 270 data points. In this diagram you can see the cumulative frequency of the load cycles. The next one of the problems was the time synchronization. This is a schematic diagram of the signal. In blue, the ultrasonic random pulses, or the blocks, 4 blocks for one half period, and in black is the low frequency amplitude of the low frequency system, and always the low frequency system comes through sigma mean. A new fiber block of ultrasonic random signals will start it, and in the fiber block always after 200 to 250 milliseconds the next random block starts, or this means after 2000 to 5000 cycles per block the next ultrasonic blocks will start. In this diagram you can see in green the low frequency signal, and in blue and in red the involved curve of the 20 kHz system. And in blue ideal system, and in red the system we measured above the test. Each data point, so each time when the ultrasonic signal has the maximum level, then we measured the signal from the ultrasonic and from the low frequency system, and it was saved. And after the test, it is possible to make one of these diagrams of the cumulative frequency of the load cycles versus the stress amplitude. Some of the tests we measured in sodium chloride, in 3.5% sodium chloride, and we used this ultrasonic chamber. The chamber has a tank for 30 liters of sodium chloride solution and a pump with a flow rate of 3.5 liters per hour, pumped the salt water into the test chamber. The test sequence, 4 parameters varies in the tests. 2 different ultrasonic sequences with sigma A high frequency, that's the maximum ultrasonic random frequency from 10 to 70, you can see here, and from 50 to 90 megapascal. 3 different low frequent signals at 1.5 and 0.4 Hertz. This means cycles per block from 2000 to 5000. 2 different environmental conditions, one in air and the second in 3.5 sodium chloride solution, both at room temperature at 20 degrees, and 4 different maximal stress levels from 340 to 400 megapascal. Now to the results. For the random signal from 10 to 7 megapascal, you can see left the results in the air and right in the salt water. And in red with 5000 cycles, for green with 4000 cycles, and the blue one with 2000 cycles. And in air, the fatigue life is increased with increasing number of cycles per block. The longer the blocks are, desto longer is the life of the specimens. And there's no significant difference in the lifetime in the sodium chloride solution. Now to the results for 50 to 90 megapascal, left air, right sodium chloride solution. The similar results for 2000 and 4000 cycles, the green and the blues, but by the blues there is less scatter than for the green ones, and the red ones live shorter than the other. And in sodium chloride, similar is to air. Additional measurements at low sigma max are in progress. In the blue condition, they are only now test for 400, and the others is in process. You can see in this image here and here cavitation, but not in the cylindric part in the measuring area. So we have no problem with cavation, and this is one of the diagrams you see before. In this case, it is for a sodium chloride test at 10 to 70 megapascal with a sigma max of 400 megapascal. And you see in the red no difference between the measuring in air. Now to the factor graphing. Left in air, right in sodium chloride solution, move at block length with 200 milliseconds or 4000 cycles per block, and at the ultrasonic random signal from 10 to 17 megapascal. And you can see here the crack initiation at a secondary phase particle, and here the same, but you can see here other secondary phase particle. Now to the conclusions. First, corrosion attack by sodium chloride solution on specimen surfaces, surface crack initiation, always surface crack initiation and no interior crack initiation. Few internal cracks are observed in air, and eventually observed two surface cracks you can see in this image. Second, the fracture surface in sodium chloride solution compared to air is rougher, more brittle, and more and deeper secondary cracks. And the fracture-graphic features allow integrating two detrimental effects: rougher fracture surface than in air with deeper secondary cracks lead to augmentation of crack extension, and anodic dissolution of crack trip probability, dismiss aggravating effects of corrosion fatigue. Thanks for your attention.